Exercise. Use the integral test to determine the convergence or divergence of the following series. My first one, I have n going from 0 to infinity of 1 over 2 to the n plus 4. If I apply the limit test to this, I see where the limit of 1 over 2 to the n plus 4 goes. That's going to go to 0, so my limit test tells me inconclusive. So this thing makes it past our limit test when we check for divergence. So I need to do more work. So what I'll do is, to use the integral test, I have to fit that to a function, positive, decreasing, and continuous. So I'm going to use 1 over 2x plus 4. That'll fit the bill. Let's take a look. I'm going to go from 0 to infinity, dx 2x plus 4. Okay, that's the improper integral. So the way we're going to solve this is to let u be equal to 2x plus 4 and just complete a u substitution. Once I do that, antiderivative will be 1/2 natural log of 2x plus 4. And then we have improper integral turns into a limit b going to infinity. Take our antiderivative, evaluate it at b, and it's 0, and take the difference. Okay, when I do that, I can pull the half out of natural log of 2b plus 4 minus natural log of 4. And then we note natural log, well, 2b plus 4 goes off to plus infinity when b goes to infinity. So we're sticking a number in here that's going to go off to infinity, or a variable in there. And so natural log of this quantity is also going to go off to infinity. So the total answer is my improper integral diverges. So we're going to have that the series we started out with diverges. All right. Let's try n going from 0 to infinity of n squared over n cubed plus 1 quantity squared. Again, we try the limit test. Well, here we're looking at a limit of essentially n squared over n to the 6th power, or roughly 1 over n to the 4th power. That's going to go to 0 as we let n go to infinity. So just hand waving that away, the limit test is not going to tell us it's divergent. It's just going to tell us we need to do more work. So we're to fit this to x squared over x cubed plus 1 quantity squared, my function on the real line. And then we take a look at the improper integral 0 to infinity of our function dx. If I look at this, I have a composition. We have x cubed plus 1 inside of the square. So I'm going to target the inside. We let u be equal to x cubed plus 1. du equals 3x squared dx. And then we isolate the dx. And now I can substitute. And we'll notice we're going to get cancellation of the x squareds, which leaves me with 1/3 u to the minus 2 du. Any derivative of this, we add 1, flip it over. So I have minus 1/3 u to the minus 1. And then I can put the x cubed plus 1 back in to get this quantity right here. We're going to take this, evaluate b and 0, take the difference, and then let the limit of b go to infinity. When I do that, we have 1/3 minus 1/3, 1 over b cubed plus 1. This b goes off to infinity. This b cubed is going to go off to infinity, driving this whole term here down to 0. So we're left with a 1/3. Conclusion, the improper integral converges, so my series converges. What does the 1/3 mean? Well, in terms of our original series, nothing at all. For the next one, let's take a look at series that's associated to 2 to the minus n as we let n go from 0 to infinity. Now, if you notice, this is the same as the series for 1/2 to the n, which is just a geometric series. And since our r here is equal to 1/2, absolute value of r is less than 1, so we know that this thing already converges and we don't really need to use the integral test. But we're going to do it anyway just to verify what we already know. The function we fit this to is going to be 2 to the minus x. So I take the improper integral over 2 to the minus x from 0 to infinity. And now note, either you look up the formula or you know the trick. The trick is going to be, I don't like working in base 2, I like working in base e. So I switch to working in base e by just writing 2 as e to the natural log 2. Once I've done that, I can pull the minus sign out in front, leave the x in the back. The antiderivative of this thing, you're going to do a u substitution with u equal to minus natural log 2 times x. And the upshot when you do that substitution is that the antiderivative will turn into, take the top, throw away the x, we divide by that, and then you're just going to be left with your e to the minus natural log 2 of x. We evaluated b and 0, take the difference, take the limit as b goes to infinity. Okay, well note this thing up on top is just going to collapse to 2 to the minus x. So when I put in b and 0 and take their difference, I'm going to have 1 minus 2 to the minus b with a 1 over natural log 2 in front. We let b go to infinity. What's going to happen? Well, natural log of 2 is a number, so this just stays where it is. 1 stays where it is. And then 2 to the minus b, if we graph that, is going to look like this. We graph 3 points. What happens at 1, 0, and minus 1? At 1, I'm going to have a half, and at minus 1, I'm going to have 2. And at 0, I'm going to have 1. So I connect the dots, and I remember that there's a horizontal asymptote at the x-axis, so that goes down like that. And so as I go out to infinity, this thing gets driven down to 0. So this term goes away, and I'm just going to be left with the 1 over natural log of 2. Okay, the 1 over natural log of 2, the only thing we need there is that that's a number. So that means the original series has to converge. We already knew that because we know how to compute geometric series.